a series of videos that provides a detailed and comprehensive explanation of Einstein's special theory of relativity. Episode 1. The Absolute Time and Space of Isaac Newton. As a preface to both the complete series and Episode 1, we provide the following introduction and summary. The series will provide both an exact understanding of Einstein's special theory of relativity and how it differs from, but is related to, the classical mechanics of Newton and Galileo. The flow of the explanation will closely follow Einstein's train of thought contained in his book Relativity, the Special and the General Theory. The scope of the video series will adhere to the words of the Nobel laureate Richard Feynman when he defines the scope of his lecture on the special theory. There are really two Einstein theories of relativity: the special theory of relativity, which dates from 1905, and in 1915 Einstein published an additional theory called the general theory of relativity. This latter theory deals with the extension of the special theory to the case of the law of gravitation. We shall not discuss the general theory here. The same applies to this series of videos. It covers the special theory of relativity. As well as observations from Richard Feynman, the series will feature contributions from Isaac Newton. This is especially the case in this episode 1, but he will feature throughout the series. The works of Galileo will make very important contributions to Einstein's discussions. And the originator of the Lorentz transformation, Professor Hendrik Lorentz, provides invaluable insights. That concludes our brief introduction, and now, who better to provide a high-level summary than Einstein himself? In Professor Lorentz's concise statement covering the theory of relativity, the professor records that a Times correspondent had asked, "What has all this to do with relativity?" And that when this query was propounded to Dr. Einstein, he replied as follows: "The term relativity refers to time and space. According to Galileo and Newton, time and space were absolute entities, and the moving systems of the universe were dependent on this absolute time and space. On this conception was built the science of mechanics. The resulting formulas sufficed for all motions of a slow nature. It was found, however, that that is the classic mechanical formulas, would not conform to the rapid motions apparent in electrodynamics. This led the Dutch Professor Lorentz and myself to develop the theory of special relativity. Briefly, the special theory discards absolute time and space and makes them, in every instance, relative to moving systems." Einstein finishes with the statement that in part tells us why the special theory is called special. "This special relativity," he said, "forming the first part of my theory, relates to all systems moving with uniform motion. That is, moving in a straight line with equal velocity." We conclude this preface with an outline of our intended audience for this video series, which, coincidentally, exactly aligns to the audience described by Einstein in the preface to his book. The present book is intended, as far as possible, to give an exact insight into the theory of relativity to those readers who, from a general scientific and philosophical point of view, are interested in the theory, but who are not conversant with the mathematical apparatus of theoretical physics. So, with those words, we are ready to begin our journey, where we follow Einstein's train of thought, a train of thought of great originality, as judged by Professor Lorentz. At the head of this train of thought was the assertion that the term relativity refers to time and space, and that, according to Galileo and Newton, time and space were absolute entities. We therefore devote episode 1 to just that, absolute time and space, as detailed by Isaac Newton. We first provide exact quotes contained in his famous Principia, the mathematical principles of natural philosophy. We then go on to give a high-level interpretation of just what these quotes mean regarding time and space. First, Newton. He opens his Principia with some definitions and then follows with a scholium, which is a scholarly explanation of terms. Starting with time, he wrote that absolute, true and mathematical time of itself and from its own nature flows equably without regard to anything external, and by another name is called duration. And very relevant to the theory of relativity, the true or equable progress of absolute time is liable to no change. The duration or perseverance of existence of things remains the same, whether the motions are swift or slow, or none at all. Relative, apparent and common time is some sensible and external, whether accurate or unequable, measure of duration by the means of motion, which is commonly used instead of true time, such as an hour, a day, a month, a year, which are examples of relative time. As to space, absolute space, in its own nature, without regard to anything external, remains always similar and immovable. Place is a part of space which a body takes up. Absolute motion is the translation of a body from one absolute place into another. We offer this interpretation of what, in general, those quotes mean regarding our universe. Empty space. It exists in its own right without regard to anything external. Light passes through space and reaches us on Earth. Bodies such as planets, stars, asteroids can pass through it. But space itself is fixed and immovable. It is not impacted by the motions of stars, planets or light. It remains the same without regard to anything external. And because space is immovable, each point within space is absolutely fixed. All bodies in motion in space move through these points. And that point is then the place or location in space of that body at that absolute point in time. And regarding absolute time, what is happening to time while light streams through space and bodies pass through it? Absolute time flows on regardless, without being affected by any of these external motions. Newton recognized that instead of this true absolute time, we must pragmatically use a relative time. This common time is relative to the means of motions of bodies, such as the Earth orbiting the Sun. This motion provides measures of relative common time, such as hour, day, month and year. How to define motion? Absolute motion is the motion of a body from one absolute place to another absolute place in space. So, if, for example, an asteroid were to move from one absolute place to another absolute place, the distance travelled in a straight line would be fixed and could not vary from the effect of anything external, such as, for example, the motion of the asteroid and its average velocity. This is another concept that is very relevant to the special theory of relativity. We will return to it later in the series. But for now, that ends our interpretation of Newton's scholium of absolute time and space. We go on to briefly discuss some points that may have occurred to you and that certainly occurred to physicists over the more than 200 years that followed the first edition of Newton's Principia. Not many issues seem to come out of Newton's description of time. It is relatively easy to accept that there is an absolute universal time ticking away in the universe that is quite unknown to us. And it is also straightforward to accept that our everyday measurement of time is indeed related to the motions of the Earth, the Sun, and many other astronomical factors. We recognize that this is not a precise method. For example, the measurement of 1 year is not precisely 365 days. But going on to space. Absolute space is immovable and consists of fixed points. This concept summons visions of a hard, rigid structure. Yet light and bodies of all sizes can pass through it. Could it be that space is quite simply empty, and that bodies such as planets pass through emptiness? This concept still allows space to be fixed and immovable, but there is an immediate issue. How does light travel through this emptiness? Just as sound waves need a medium to travel through, such as the air or water, do not the electromagnetic waves of light also require some sort of medium through which to travel? The existence of a luminiferous ether was proposed by physicists to act as the medium for transmission of electromagnetic waves. This theory was to play an important role in Einstein's development of the special theory, and towards the end of the 19th century directly involved Professor Lorentz. He explained the theory of ether as follows. It was reasoned formerly the ether which fills the space of the universe and is the carrier of light and of electromagnetic phenomena. The ether is thus the medium for light, but does it not interfere with bodies? Using the Earth as an example of such a body, he says there were good reasons to assume that the Earth was entirely permeable for the ether and could travel through it without setting it in motion. Lorentz then poses a question that directly brings us to the first chapter of Einstein's book. How can we measure the distance between fixed points in space, such as the distance travelled in a straight line by our earlier example of an asteroid in motion between two places in absolute space? He reasons that if the spaces of the universe are filled with an ether, let us suppose with a substance in which, aside from eventual vibrations and other slight movements, there is never any crowding or flowing of one part alongside of another. Then we can imagine fixed points existing in it, for example points in a straight line, located 1 meter apart. points in a level plane, extending out into infinity. If consequently one of the points is chosen as an original point, we can, proceeding from that point, reach any other point through 3 steps in the common perpendicular directions in which the points are arranged. The figures showing how many meters are comprised in each of the steps may serve to indicate the place reached and to distinguish it from any other. These are the coordinates of these places. At this point, we allow Einstein's train of thought to take over. Episode 2 of this series will take up his thinking from the first chapter of his book, where he starts to define how to specify a place in space, and much else, including the Galilean system of coordinates and the law of inertia. We will also see what happens when Einstein throws a stone out of a railway carriage window. If you enjoyed this video, you are invited to join our community on locals.com. This link will take you directly to our site.